I'm going to list the 4 conditions again for binomial. Fixed number. Fixed number of events. Must be independent of each other. Each event must have 2 outcomes. We call them success and failure. And the probability of success must remain the same through each case. If you have an event that's a binomial that meets these criteria, if you want to find the mean of that, then it's the summation of x times piece of x. And the standard deviation will be the summation of x squared times piece of x minus mu squared. That's how we calculate each one. Where this method is going to be handy or ugly, depends how you look at it. This method is nice when you have a small sample. You have a test of 10 questions. But let me rephrase the question. Let's say we have a test of 50 questions, not 10, 50 questions. It's a multiple choice test. Let's say 50 or 100. 50, let's make it even 100. We have a test that has 100 questions on it. And each question has 4 answers. Only 1 correct answer to each question. And the other statement I'm going to make, assume the questions are independent. Well, let's see why I wrote all this stuff there. And the question now, what is the probability? Find the probability of somebody passing the test, which means scoring more than 60. We'll define 60 as passing the test. You're getting a D or D minus. Why did I list all these statements? Well, I got a lot of things on the top here. Let's see. What test has 100 questions? That's the first condition for binomial. Do you have a fixed number of questions? In this example, yes. What's the fixed number? That's 100. That's your n. Each question has 4 answers, only 1 correct answer to each question. So you have fixed number. The last statement says the questions are what? Independent. We do have independent. I stated that. So test number 1 passed, test number 2 passed. I listed that here. Each question has 2 outcomes or reducible to 2. What are the 2 outcomes? Correct / what? Wrong. Success, failure. I'm going to define correct or success, getting the correct answer. Failure, getting what? The wrong answer. And what's the last statement? The probability of success must remain the same. What is the probability of getting the correct answer for each question? 1 out of 4 or 25%. So I did satisfy the conditions for binomial. So if you want to do the problem the correct way, the true way of doing this problem, it is a binomial experiment. I'm going to define x as a success, the number of correct answers. So my table will look like this, x and the probability of x. Could you actually have a 0 on that test? Is it possible for somebody to get a 0? Sure. 0, 1, 2, all the way to what? 60, 61, 62, all the way to what? 100. These are all possible outcomes. And if you want the probability of getting at least 60, that means you have to find the answer to what? 60, 61, 62, 3, 4, 5, 6, 7, all the way down to 100. How many values you have to calculate? 41 values. And how do you calculate the value for each one? You have to use this equation. So you got to find the value for each one. And n here is 100, and x is changing. P is 0.25. To the x power, q is going to be the wrong answer, 0.75 to what? 100 minus x. And you got to do it for the 60 when x is 60, x is 61, x is 62, x is 63, and so forth. You got to find all these answers and add them. Now imagine if I said to you also, you know what, while you add it, since I'm interested in that, let me find the average. What is the average for the class here? Well, then that means you got to go back and find the answer to each one of these. All 100 of them. Why? Because the average is the sum of x times piece of x. So I go, oh boy, I got to do all 101 values here. Find the answer to each one, multiply them, and add them. Oh, while you're at it, since you got nothing better to do, let's find the standard deviation. I need to add another column of x squared times piece of x minus mu squared. You know where I'm going with this, because nobody in the right mind is going to do this. That's too much work. So is there a way you can do this problem, get a result very close to the real answer without having to calculate this 100 times or 101 times? And that's where the normal approximation to binomial comes in. It says we can actually treat this problem as a normal distribution and solve it as normal. But before you can say, yes, we can do it, there's a criteria you have to meet. Can I use, here's the question, can I use the normal approximation here? Can I use that? And the answer to that is yes if you meet these conditions. What are the two conditions? If n times p is more than 5 or equal to, and n times q more than or equal to 5. If that's yes and this is yes, yes, you can use the approximation. And the bigger the number, the farther from 5 it is, the better the result, the closer the result is. So in this example, n is 100, and p is what, 0.25? So what do you have? You have 25. Is 25 bigger than 5? Yes. N times q, 100 times 0.75, which is what? 75. Is that bigger than or equal to 5? Yes. So both of these conditions are yes and yes. Since both are yes, we can use the approximation. I should use the word the normal approximation, because we're going to treat this as a normal distribution problem. Well, if you recall from last homework, when you did the normal distribution, we always gave you the mean and the standard deviation. Well, you don't have the mean or the standard deviation here. If you're going to treat this as normal distribution, you need to have the mean and the standard deviation. So to get the mean, it's going to be n times p when it's normal. And in this case, n is what? 100 times p, which is what? 0.25? That's 25. What does that mean? If you close your eyes and you just picked at random, which answer? You should guess 25 correct answers on that test. So if you take that test, you get a 5 on it, boy, you're unlucky. Because even if you have no idea what the subject is, if different language, you should get around the 25 for guessing. Mu, not the standard. I wrote sigma here. That's the mean. Where's my eraser? Mu is n times. Sigma is the square root of n times p times q. And in this example, the square root of 100 times 0.25 times 0.75. And it says 4.33. So step number 1, can I use the approximation? Yes. Step number 2 now, since we agreed we can use the approximation, let's find mu and sigma. Step number 3, step number 3, we're going to treat that as normal distribution, the problem now. So step number 3, here's the problem, and it's going to be treated as normal distribution, because we're using the approximation. And what is the mean for that? The mean is what we calculate in step number 2, which is 25, and the standard deviation I'm going to be using is what? 4.33. And we wanted the probability of somebody passing that test. We define passing to be what? 60. So 60 is somewhere here. But now I want you to think about this. If you're doing a histogram and you're graphing, remember the histogram is a bar graph, and the 60 is right here. You want to graph how many people in the 60. Where would you start the 60 at? This is the 59. This is the 58. This is the 61. The histogram has no gaps in it. Remember that? So the 60 should start where? Right there. It should start at 59.5, and it should end where? At 60.5. So I need to make an adjustment to this value. Now the question, let me go back to the question. Did I say what is the probability of somebody scoring more than 60 or greater than or equal to 60? What was my question initially? Greater than 60. So 60 is not good, according to my statement. You have to get 61 or higher. So since 60 is not included, where does the 60 end? At 60.5, so this should be 60.5. You're always going to add a 0.5 or subtract a 0.5 to that number. If I had greater than or equal to 60, that means the 60 is included, and I will start this where? At 59.5. Oh, excuse me, my blood number. They can leave a number for me. So 60.5. So here's my histogram, not my histogram, my normal distribution right there. There's a 60.5. Step number 4, I need to calculate the z value for that. So step number 3, either add / subtract. It depends if the value included or not. 0.5 to the x value. Adjustment, make an adjustment to it. So in this case, I'm going to add the 0.5 because 60 is not included. I'm going to the right of that. That's 60.5 minus mu, which is 25, divided by what? 4.33. And the z value is always 2 digits. And the answer is 8.14. I don't even have to look at that table now. We go at step number 5, we go to the normal distribution table. I wanted the area to the right of 8.14. Your chart says if the value is more than, what is it, 3.5? Is it 3.5 or more? To use what? 0.9999, is it? Is that what they're telling you on that table? Look at the table we gave you. The highest z value on that table is 3.99 or 3.5, I think, right? Look at the positive z score. Isn't the biggest number 3.5? Yep. And it says if the value is 3.5, to use what? 0.9999? Yep. So this area here, 0.9999, the one to the left. So what do you think the area to the right? What is the probability that the z value, the score, x will be greater than 60? That tells you have no chance in hell. Why? Because the answer to that is 1 minus 0.9999, which is 0.0001. One person out of 1,000 might get that number, pass that test. 1 out of 1,000 people that take it. And that's how we do the normal approximation to binomial. It makes the problem a lot quicker and easier. Let's take another example. I'm a huge Patriots fan, you probably know by now, or Red Sox fan, any Boston fan, since we're from Boston area. Let's take the NFL. National Football League. In overtime games, in National Football League, overtime, when the game went to overtime, if you watch the game, they usually come back and say, okay, we're going to flip the coin to decide who's going to start first. They monitor 431 overtime games. That went to overtime. And here's what they notice. The team that won the toss, that's a W here, it looks like OO. The coin toss went on to win the game. $235 games. Now your chance of winning when you flip a coin is supposed to be 50-50. 235 team won the toss, won to win the game. So if your chance is 50-50 when you go overtime, because if the two teams are close enough, they went to overtime, they must be close enough. The chance of winning, each one's 50-50. Then if that's the case, what's 50% of that number? We actually expect, we would have expected to see what? Roughly 215.5. We can't have a 0.5, but 50-50 wins in 431 games. 215.5 wins. Why? Because the probability of winning the game is the same as the probability of losing the game, which is 0.5. You have 50% chance. And what I'm interested in is something magical about that number, the 235. So what is the probability? If we repeat this process again one more time, 431 games, what is the probability of at least 235 winning games? By the team that won the toss. So we're studying that number to see if there is anything like something funny about that number. At least winning 235. I mean, it is possible that if you have 431 games, the team that wins actually the toss wins every game. It is possible. It is also possible that the team that won the toss out of the 431 never to win a single game. So we'll define X as win here. So, and this is the probability of that. You could go from 0 win to 1 win to all the way to where? 235, keep going to what? 431? That's all the outcomes. From 235 to 431, there's a lot of numbers to calculate there. I got to find the probability of each one of them and add them. No way. I don't have enough time for that. Even if you gave me a week, I could do it in a week. I could do it probably in 2 days, but that means I got to go sit somewhere, be quiet, and just calculate each number and hope I don't make a mistake pushing the button on my calculator. So I want to see if I can use the normal approximation. Step number 1. Can we use, bless you, can we use normal approximation? Can we use the normal approximation method? And to answer that, you got to make sure n times p is greater than or equal to 5, and n times q is what? Greater than or equal to 5. N is what? How many games? 431 times 0.5, 215.5. Way more than 5. I'm good. N times Q. 431 times 0.52. 215.5. That's also more than 5. So yes, we can. We can use the approximation. Step number 2, what do you want to do? Calculate the average or the mean and the standard deviation. The mean is what? N times P. 431 times 0.5, 215.5. The standard deviation, N times P times Q. 431, 0.5, 0.5. Take the square root of that, 10.38. So here's step number 3. I'm going to graph it. We're going to treat it as normal distribution with the average of what? 215.5. Standard deviation is what? 10.38. And the question, what is the chance, let me go back here, of a team winning at least 235? What does that mean, at least 235? At least 235. Is the 235 included? Yeah. 230. How about 236? So it has to be 235 or higher. We're looking for x is greater than or equal to 235. So the 235 is going to be somewhere here. We're looking for that area. Remember, we have to do an adjustment on step number 4. We're either going to add 0.5 or we're going to subtract 0.5 from x. If you look at the 235, that's step number 4. If you look at just the vertical strip, the bar graph for the 235, the vertical strip for that, where is it going to begin? From where to where? For the 235, if you were to do a bar graph. Any answer? Could it be 234.5 to 235.5? So if you're trying to graph like a histogram, when you do that 235, you go, that starts at 234.5. These are the boundaries for each one. You subtract 0.5. Add 0.5 to that. Now, is that 235 included? Since it's included, I'm going to use what value here? X for my case is going to be the 234.5 because I am including that piece. So again, this is the 235, 234, 236. The 235 starts here. Well, a little bit farther here. The 236 starts here. So if you want 235 or higher, you better start from this point on. So x is actually 234.5. And now step number 5. We're going to find the z value that goes with the 234.5. So what's the z value equal to? X minus mu over sigma. My x is 234.5 minus, what was the mean? 215.5. And what was the standard deviation? 10.38. Do the math. I think that's a 1.83. 234.5 minus 215.5. It's 19 divided by 10.38. 1.83. So now we're looking for the probability of greater than a z value of 1.83. The team that won the toss will win at least 235 games. Let's see what the chance of that happening. So look at the positive z-score chart. Find the answer for 1.83. 0.9664. I'm looking for to the right of that. That'll be what? 1 minus 0.9664, which is what? 0.0336. That says 3.36% chance that the team that wins the toss at the beginning of that overtime, there's a 3.36% chance will win more than 235 games at the end. if we count out of 431. It's not a high probability. So we don't have to calculate all these numbers. And that's the final piece of the normal approximation to binomial. That's it. All the examples you're going to be doing is you have lots of cases to calculate. Use your brain, be smart. The first question is, can I use this method? If they answer no to one of these, you cannot, and you're stuck. You got to do the table, go value by value, add them all. That's the only way to do it. There's no shortcut. The only shortcut you might find, you might be able to go to Excel, have Excel do the calculation for you. There's an NCR and NPR on Excel, so you can do that. But if you don't have that, you're in trouble. You got to do all these numbers by hand: 235, 236, 237, 238, 239, 240, 300, 350, 400, 420, 430, 431, all the way down, and add all these numbers.